Now we're going. So capacitor. What is a capacitor? Does anybody know? Yep, it builds up a charge. Is that what you're going to say? So, yeah, it's a device used to store charge. Oh my gosh. Used to store charge. Which, when it discharges it, it expresses itself as a voltage or as currents, things like that. It is quite simply two pieces of metal slapped together with some sort of insulating material. It's crude, but that's all it is. It's just the ability of these two pieces of metal. The closer you put a piece of metal together, you can build a charge up in between them. The farther apart, obviously, you have more capacitance because there's more that it has to overcome to be able to store this charge. But you can store a capacitor depending on the material in between it if the plates are this far apart. So quite simply put again, it's just two plates that are separated by some sort of an insulating material. The way to look at these guys is they're going to look like this. So we got metal through here. And we have insulation. Some capacitors have a positive and negative charge to them. So we refer to those, we have electrolytic and non-electrolytic or ceramic type capacitors. And the idea with those is on a schematic, we'll see capacitors that look like this. This is an electrolytic. And this would just be a ceramic. Now, with the electrolytics, they do have a polarity attached to them. Just how they're made, how they're doped, there's an inherent polarity to them. If you put a voltage on backwards, you're going to break them down, they're going to explode, which we'll actually go through, and we will show some of those later. Apologize. I don't know why that was turned up. Okay, so we have an electrolytic and we have ceramic. But both of them function the exact same way. The only difference is how they're made out of. The electrolytic, they're really good for when we're filtering in low frequencies. The ceramics are really good for timing constants. Part of the problem with the electrolytics is we have a wider range of values for these guys, but they are very, very leaky. So one thing to remember is when you get into your labs, when you put a charge across an electrolytic, it's going to allow a small amount of current to flow from it, which is in a sense going to be discharging whatever it's stored to it. So it's going to affect your timing constants, things like that. The ceramics are able to hold their charge a lot better, but I think they have a smaller range of values that we can get to, just the different manufacturing processes, things like that. So they both serve their purpose, but understand you do not want to use an electrolytic cap when you have something that's involved timing. Now, the reason we talk about timing is in the digital world, timing is everything. It's all about how fast can something change states. It's all about how fast can we get information transferred. Transistors are used to store information like in RAM. It's used to store the ones and zeros. You have a capacitor that stores a charge that keeps the transistor biased. That's how RAM works, or how memory works. When you turn your computer off, because you have your random access memory versus your hard drive, your random access memory is just a storage place that your computer uses to store information in between programs, load up graphics, things like that. When you shut off power, it loses all the power to it and it forgets everything. So when you reboot your computer, you are in a sense clearing out your RAM. But your hard drives, they have, like an SSD, they have individual memory cells that are stored with tiny capacitors. And capacitors are the easiest things to build. Like I said, they're just literally two pieces of metal with an insulating material between them. They do at some point, but it's years. They're all leaky. The electrolytics are just even worse. Like, you can watch them and they will discharge within a few hours. Ceramics, you have like 5 to 10 years for some of them. Yep. And so that's why every so often they'll go through and they'll refresh, and while they're connected up to power, it's constantly refreshing all those charges. Yep, if you don't play it. Yep, those are one of the, yeah, I remember hearing stories. I actually own some of those, not the originals, mind you, but when those games came out, they were able to store your saved game, like, that was amazing for people. It was unheard of. People didn't know that. Yes, because you have to rebeat the level to the same spot. And there's still some games that are, like that. Like with a regular Nintendo, it doesn't save it. You turn the Mario 3 off when you go away, and you have to start back over at level 1. So there were times we would just leave it on just because we didn't want our save game to go away.
So there'd be games that I could save, but what if it doesn't save this time? So I'll leave it on anyway.
Yep. All right. So one of the things that we have here is when we build our capacitor, there's several factors that we're going to take into account, but the biggest ones specifically is this. This is the distance between the two plates. We'll talk about here in a little bit about a formula about what this entails. So the farther apart the plates are, the smaller the capacitance. We also have this area. So with the surface area, we have to think about it as what's being overlapped. So it's this front here. How much surface area are we sharing between the capacitors? That's the other big key factor that we have. The other one is what type of insulation are we using? So the key things is what type of insulation, how far apart are these metal plates, and what kind of surface area are we dealing with? Those are going to be the key factors in determining how much capacitance an object has. So how we solve for these guys is capacitance is measured as charge over voltage. So who remembers what charge is measured in? Coulombs. You can also find it using joules, which we'll talk about later for energy. So capacitance is equal to the charge, the coulombs, which is the number of electrons that are physically present, divided by the voltage. So 1 farad, which is what capacitors are measured in, is equal to 1 coulomb divided by 1 volt. So 1 coulomb basically of charge that naturally builds up because of electrons, divided by the voltage, gives us the farads. Now typically when we measure farads, we're going to be... Do what? Say that one more time. Oh yeah, 1 well, remember coulombs is measured in coulombs, which is a capital C. So what we're measuring versus the unit of measurement. Yeah, like I said, this is kind of the complicated stuff that we have to remember. Yes, I agree. And in electronics, they didn't do a very good job at renaming things. So, if we were to look at this with a circuit, we have a voltage supply and a capacitor. We have 11 volts we need to know what our capacitance is. And we have a charge of 1.98 nanocoulombs. Coulombs is literally the amount of charge that's on an item, and it's based on the number of electrons that are present. We can't measure with it, but a lot of times we can calculate what it would be. So how many farads is in this guy? That's kind of a standard cap. It's a tiny value, but for what we use for, the majority of what we use is micro, nano, or picofarads. That's the majority of what we're going to be using. 180 farad capacitor. You'd see those in like power industries where they have to store huge amounts of power. They're trying to get things to charge slow, charge fast. That's when you'll see those. 1.98 nanocoulombs. That's one thing too, is when we're dealing with these, we're going to be dealing with about a whole nother set of variables that we haven't gotten used to. So in DC, we talk about microamps. That's about the smallest we go. When we start getting into the AC, we're going to be starting to see things very common with the nano prefix, with the micro prefix, and also pico, which is the small p. Okay, so another problem is we're trying to find how much our voltage is on this guy. We have 1.8 farads and 16.2 coulombs. How much voltage would we have across this circuit? Hmm? 29.16. So remember, capacitance is equal to charge over voltage. We're solving for voltage. So we have charge over capacitance. Because we multiply both sides by V, divide both sides by C. 9 volts. For the first one? Should be pico? Yeah, it should be pico. Because remember, we have milli, which is -3, micro, which is -6, micro nano is -9, and pico is -12. Yes, and that's the problem too, is if we throw in those values, so yeah, it's supposed to be pico. PICO. Yep. One of the other formulas that we can use to calculate this is the amount of work that an object can do. So work is equal to 1/2 times the capacitance times the voltage squared. We're not going to use this a whole lot, but there are some questions in the homework that deal with how many joules of energy is used in a capacitor with so much capacitance, so much voltage. Yes. When it's by itself, we're representing capacitance. When it's tagged onto the end of a value, that's referring to coulombs. This is to find the amount of energy. Basically, the amount of energy or the amount of work that a capacitor can do. It's based on its capacitance and the voltage. How much stuff can it move? Like I said, it's not something we use a lot, but we do have different ways to solve for it based on what parameters we're given. Because we can measure the amount of joules, we can measure the amount of energy that gets released when capacitors are operating. And we can measure capacitance, we can measure voltage. We just don't have those here at school, so we don't deal with those a whole lot. But some places do. Okay. So kind of coming back to this idea, I just wanted to introduce real quick. These are some rudimentary, fundamental ways of how capacitors work. Based on the biggest one is based on their charge, based on the capacitance, and based on the voltage. So the biggest thing to remember is this formula to start with. The capacitance is equal to your charge over your voltage. I believe so, but not with the stuff that we have here. Very, very expensive, very, very specialized machines. Yeah, it's primarily a calculated value. All right. So moving back to where we were with the with how a capacitor is physically set up. So how we have it is that our capacitor is going to look something like this. Well, the formula to be able to calculate this, and this is going to become important on understanding how these things work when we put them in a circuit. So first off, we have the area. So we have the surface area that the metal plates overlap. We've got our metal plates. And we have the insulation. And those are our primary factors in determining how much capacitance it has. With these, you could build and design your own capacitor if you wanted to. If you wanted a 180 farad capacitor, you could build one. Might, depending on how it is, it might be fairly large, but you can figure it out. Okay? So with this, the formula that we have for physical characteristics, because that's what we remember, is the physical characteristics of a capacitor. The capacitance is equal to the area times ER, which I can't remember the name for it right now, but basically what this is a constant based on what type of material it is. How conductive inherently is the material. Times 8.85 times 10 to the negative 12. And then this whole thing is divided by distance. So what we get is we get farads per meter, and then once we do that, we can break it down into what the capacitance value is. The reason that this becomes important, like I said, is the physical properties of when we connect them. So some common values that you'll see to the negative 12th, yes. The pen didn't take the one. So A is our surface area. D is our distance between the plates. C is the total capacitance. Yes. And the ER value, it's the dielectric factor. That's what it was. So ER is the dielectric factor, which is basically how well does a material do at conducting electricity. So what would you think would be, thinking of that how much it can conduct versus how much it can resist, giving that a value of 1.0 is common air. So this is if we had two plates of metal just hanging out here, That's the 1.0. If we had another material, let's say Teflon, do you think Teflon would be more of an insulator or less of an insulator than air? It'd be more. So that's what this is. It's a measurement of basically how good of an insulator is a material. Okay? So Teflon is 2.0. Paper, which has paraffin wax on it, is a 2.5. This is primarily what electrolytic capacitors have in them. They're sheets of metal with paraffin paper wrapped around them. Oops. The next we have is oil. And the reason this is important, because like I said, you could design your own capacitor just by designing it with these different materials. The next we have is considered a 5, is mica, which is like a sand material. You jump up to 7.5, you get glass. And the last common material we have is ceramic. And what do you think ceramic's insulation properties are? Seriously? Oh my gosh. Has a factor of 1200. That's why ceramic capacitors are so good. That's why when you see up on power poles, anything that's on the power pole that is touching those high voltage lines is ceramic. Because ceramic is a very, very, very nice insulator. It's one of the better ones we can get. Mm-hmm. Just hang on to them. They're cool. But yeah, they moved from glass, because glass at the time was 7.5. When they started using ceramic, they realized, it jumped it up to 1200. That's why you can have on these high voltage lines, we don't have a lot of high voltage ones. If you go downtown, heading towards H&H Dive, heading towards the concrete plants that are out there, there is a bunch of high power voltage lines running to the old Hoku plant. Even with those great big lines, they'd be sitting on a small ceramic capacitor or insulator. Yeah, heading down to Malad. All those power lines that are running down next to the freeway, those are all high voltage lines. And if you can get to the point where you could stop and look, get a pair of binoculars or spotting scopes, you're just going to find a little thin ceramic insulator between it and the pole. Huh? So the idea behind this is how a capacitor physically works. So depending on the material it's made out of, how far apart things are, and what the area is going to determine the value of the capacitance. So with our formula, remember what I said earlier about distance. What happens when our plates move farther apart? Capacitance goes down because distance is going up. Our denominator's value is getting larger and larger, so the overall value is getting smaller and smaller. Okay? Mm-hmm. Yep, they tell you what kind of material. Or, yeah, ER is your insulation factor, basically, your dielectric factor, the opposition to the electricity flowing through it.
On the quiz, so they'll tell us the material, are they going to tell us the dielectric factor too, or do we need to refer back to this?
You would refer back to this. I think on some of them we do give them, but this will be your reference for it. So the other idea is, so let's say we had a capacitor. Let's say we wanted to increase the capacitance. What could we do? You can make it smaller, okay? How would we do that if we wanted something like a variable capacitor? Because we have variable resistors, right? You guys have seen those. All we do is we adjust a brush and a wiper onto basically a resistive band. You could adjust the distance. That's kind of hard to do because most of the time these are set with the material. Oil, you can kind of get it to compact a little bit. Paper, a little bit. But what if it's like, Teflon or stuff? Does that compact very well? No. So now we got a problem with we can only compact it so far. So what would we need to do to be able to make it a variable capacitor? Change the area. So what happens, and a lot of this is you guys will see and understand too. I have some examples I'll bring in tomorrow. I'm not sure where they went. One of the other instructors has them. But you're going to learn this in RF. Capacitors are one of the easiest things to get to change. Okay, if you want, versus resistors, because those are all your knobs and dials. A capacitor, you can actually change the area by having a device that has plates. One of them is fixed, one of them is on a pivot point. As you turn it, you're now increasing more and more surface area into the capacitor, increasing the capacitance. That's how you tune a radio. Inductors you can, but basically you move the core of an inductor up and down. But capacitors are by far the easiest. They have lots and lots of plates that they interlock and creates more and more of a surface area, which increases your capacitance, which then changes frequencies, which we'll be talking about next semester. So the easiest thing with a capacitor to do is change the surface area by creating it somehow with fins that overlap each other. And when we do those, most of the time they're going to be an air insulated capacitor. So I'll show you some. We have some in the lab that we've used before. When you get into the fourth semester, you're going to talk about these guys a lot because, like I said, the variable capacitors are a lot easier to get, a lot cheaper than variable inductors. So, if you have a plate, like I was talking about, so you have one plate sitting here, you have another plate that's sitting over top, where is your surface area? Where they overlap. Think of a Venn diagram. So this area here is the surface area of this capacitor. So as you're thinking with these fins that go overlap, so first you start off, you have a very thin sliver, and then as you turn it, you're going to get more and more of that's covered up. So if we did this versus this, which one's going to have more capacitance? The one on the right, because it has more surface area. What if we were to take this guy and spread it farther apart while we were increasing the area? If we were increasing them at the same rates. So if we're increasing the distance the same much as we're increasing the area, they would stay the same. But generally, the distance is going to be a lot bigger of a factor than our area. Because we're talking very, very small amounts of distance changes can affect our capacitance. So as our distance increases, our capacitance decreases. When the area increases, our capacitance increases as well. So this is kind of the relationship that we need to learn and understand with capacitors. So basically, how does this apply to capacitors? Okay? In circuits. So if we have a circuit, and we put one capacitor in there, we're going to have a certain amount of capacitance in the circuit. It's just simply the value of the one capacitor. What happens when we put a capacitor in series? What do you think?
You're going to have to treat it like it's in parallel.
Mm-hmm. We take the reciprocals. Okay, but why? What are we physically doing to this circuit now? We're changing the capacitance. Okay, so think about as we're drawing this, what do we call this measure between the two plates? Distance. Okay, that line is essentially a short electrically. They're in the same place. Okay, so what have we done now? Now that we've got this guy, we have distance there. What have we increased on our circuit? Oops, sorry. Not the area, the distance. So now, when we put capacitors in series, what we've done is we've essentially increased the distance between the two metal plates. We've added more insulation between them because we also have the line that they can travel through the wire, but now we're going through twice as much. Because now we're going through, twice as much material for our capacitors. So our capacitance is going to go down. And so like what Zach was saying, when we have capacitors in the series, we're going to treat the capacitance as if it was resistance in parallel because they're affecting each other. So as we increase distance, capacitance goes down, and that's how we're going to find this. To what? Yes. You're adding them. So in series, the capacitance is going to be equal to yes. If there's two capacitors, we still can. Okay? Versus this, because now we still have the same distance, but now we've doubled the area. Because now we're exposing more area to be able to hold charge. So in this case, we would add them. And that's why, because of their physical characteristics. That's why it's important that we understand what's going on. Not so much the formula to get there. There's a couple questions about this, but the idea is what happens when I do something. Okay? We can't really change the material it's made out of. So that's not even a factor. This is a constant. We're not going to be changing that. The only two things that we have available to us is area and distance. Yeah, the distance basically put them in series has a larger effect. That's why when we see the reciprocals, we're going to still follow the same rules. So this is where your thinking has to kind of shift. When you're dealing with capacitors, they are the opposites of how resistors work together. So in series, we treat them as parallel. In parallel, we treat them as if resistors in series. Like I said, it's kind of hard, but you got to wrap your head around that concept when we're dealing with those. Inductors are going to be more like the resistors. They don't have anything special. They're just coils of wire at that point. But this one, we have a physical separation between these. All right. So looking at these guys, so we have our circuit. So in our circuit, we have our voltage is equal to the charge over the capacitance. Same formula that we started with earlier. The way we can prove that this works, not only understanding the distance, but if we have a circuit and we add in another capacitor. Okay? The voltage total has to equal the voltage of capacitor 1 plus the voltage of capacitor 2. Same thing with series. with resistors, okay? Everything in series is going to have a voltage drop. They all have to equal up to the total voltage. In a series circuit, the charge is equal for each of the capacitors. Each capacitor will charge up to the same with the number of electrons that they have, but because they have different capacitances, they're going to charge to different values. So the charge, so remember like in a parallel circuit we have voltage. Voltage stays the same in parallel. With capacitors, the charge stays the same. So they will all charge up to the exact same number of electrons basically on one side of the capacitor, but because they have different capacitances because of the distance, the materials, that kind of stuff, the capacitance will be different, but the charge will be equal. So to find for each of these voltages, we are going to substitute these formulas. So our voltage total is the charge total over the capacitance total. Okay, all we've done is make this substitution. That is equal to the voltage of capacitor 1 is equal to the charge of C1 over the capacitance of C1. Right? Because all we're doing is we're just rewriting this original problem in terms of our charge. That is equal to the charge of capacitor 2 over the capacitance of 2. So right now all we've done is we've just turned it into, instead of voltages, we've turned it into charge and capacitance. The idea is we're going to prove that the capacitances in series we treat them as the reciprocals. And now we factor, because we're trying to isolate the Q, because we know that these Q's are equal, because I'm telling you, because they all have access to the same amount of voltage, they're only going to charge to a certain amount. There's only a certain number of electrons that are moving in the circuit. They're trying to grab hold of as many as they can, and they're both going to get an equal share. Yes, I believe that's where that value comes from. There wasn't a whole lot of explanation I found on what that number was. Just this is how you find it. So we're going to factor out our charge. So our charge total is over our capacitance total is equal to the total charge okay? What we're trying to do is we're trying to simplify this problem down to be able to solve for total capacitance. That's what we're trying to solve for, is this guy. Next thing we want to do is we want to get rid of the Q, because we want to solve for the total capacitance. So we divide both sides by our charge. So we get on this side, they're going to cancel each other out. And we're left with the charge total over the capacitance total times 1 over our Q. And now remember, in the series circuit, they are equal. They're going to cancel. So we're left with the reciprocal of our capacitance total is equal to that. We solve for the capacitance total by taking the reciprocal of both sides, and we end up with the reciprocal method for our formula. So the whole idea and the whole thing that we're trying to do here is we're trying to get rid of charge. because charge is a hard thing to try to measure. It's a hard thing to get. And in our lab, we can't work with charge. We don't have any equipment necessary to calculate for it. So we want to try and eliminate it from our equation altogether. It's still there, but we just don't care about it. Okay, I know I'm getting a lot of blank spaces. It's a lot to kind of process. But the idea is, in a series circuit, the charge is equal across everything. The total charge is going to be what each capacitor charges up to. We don't really know and can't measure this value with the equipment we have in lab. So we need to be able to find a way to remove this part from our equation. And this is how we do it. We substitute everything in terms of charge, we solve it down, and we get back to where our capacitance is going to be equal to the 1 over our capacitor plus 1 over our capacitor. The way getting through this is not, you don't need to know, but I just wanted you guys to see that we can get rid of it if we don't need it. There are ways to do that. So the big point is this part right here, coming down with our capacitance, how do we solve for it? And that the charge is equal everywhere in the circuit. Resistance? So in DC, capacitors will have infinite resistance. Because what are they? They're an open at this point. And when you measure across an open, you get all the voltage that it has access to. And so what's going to happen is these guys are going to charge, and they're going to take some time to charge, and once they do, they'll stop. And after that, they will be treated as an open, and there will be no DC current flow in this circuit at all. So if we hook them up with a scope, we could actually see this. Yes?
So if you're using capacitors, they have to be set up in parallel, else there won't be any current.
Well, once they charge up, that branch is going to open up anyway. Yeah, it won't. If it arcs across, we've got a problem because then it's discharging the voltage. But what it does, it's going to store that voltage onto that capacitor until it gets used. That's another thing you guys will be testing in the lab is you're going to be charging up capacitors and then discharging them through your meter. You got to remember they're only going to charge up to about 10 volts or so it's not going to do anything to your meter. But the idea is that we can track these guys. So computers, when you're booting up chips, one of the things you'll find in 5th semester, I believe, when you're powering up chips like a PIC, a programmable controller, or like even our Arduino or things like that, one of the things it has is there's a little brownout detector circuit. And so what happens is that it has a capacitor built into it to charge. In case it loses power, it discharges and tries to keep itself running for as long as it can. Sometimes they're only milliseconds, sometimes they're less than that. Sometimes you can get them to charge for like a second. That just helps that if your power drops off, it can keep itself regulated. Well, what you have to do is you have to charge this guy up. So as you're charging up, you don't want your circuit, your controller, to be drawing power. So you'd run it through this timing circuit. So this would be connected into the pins of your chip. So what happens, you would charge it up, and then as soon as it hits a certain voltage, this is going to open and give you either a high or a low on your output. When that chip receives the low and it has full power, everything's going to power up properly. If you don't put a little bit of a delay on that pin, it's going to fire up in a random state. But you want it to turn on in the same exact state every single time, and so this is what you do. Yep. Yep. Because it charges up, and then it'll discharge a little bit, and then it'll charge back up. That gets into the end of next semester. But the idea behind it is we're charging a capacitor to give us a value, and once we have that value, it's going to open up the circuit, which then would give us no voltage across a pin, which in the digital world is good because it creates a delay. There's sometimes we want delays, and there's times we don't want delays. This is the times on startup is we want certain things to be shut off, have no control, but we don't want to have to go in and after we turn it on, then we plug in power to the chip, or then we plug in power to the main programmer, things like that. This is a way to automatically do it just using components with no programming. So that's the other idea too, is we're teaching you guys how to hard code things in, whereas where you'll be then programming these delays, these functions in later. Okay. Let's go ahead and take a break. We'll get into some of the math behind these guys here in a minute. We'll start working through some of these problems.